Welcome to today's webcast entitled Spectrum Analysis Fundamentals, brought to you by Keysight Technologies. I'm Tim Cole. Let me introduce today's speaker. Dave Engelder is a strategic planner for Keysight Technologies. Dave earned a BSEE from University of California, Santa Barbara in 1979. He joined HP in 1980 and has devoted his 37-year career to RF and microwave measurements. Dave has held customer support, R&D, marketing, management, and strategic planning positions in HP, then Agilent, and now Keysight. In his current position, Dave digs deep to understand customer measurement needs, consults with management on investment decisions, develops roadmaps of future products, and works with R&D to guide development of new spectrum analyzer products and solutions. Now on to today's presentation on spectrum analysis fundamentals. Dave, the floor is yours.
Hi everybody. Welcome to the Signal Analysis Fundamentals webcast. This is part of Keysight's RF Engineering Education series. My name is Dave Engelder, and I've been with the company for 37 years, pretty much all of it in RF and microwave instrumentation and measurements. Our agenda today is going to start with an overview of the frequency domain, then move on to theory of operation. How does a spectrum analyzer work inside? We'll talk a little bit about specifications and which ones matter the most to your application, and we'll wrap up with a potpourri of features. So what is a spectrum analyzer? Well, those of us who work in the electronics field, we know that we can't see with our own eyes what's going on with signals in the electrons and currents and voltages of the field that we work in, so we need instruments to help us see what's going on. A spectrum analyzer is going to do that in the frequency domain. It'll display amplitude versus frequency. Take a look at this display down here, and you see that at low frequencies to the left-hand edge, we have very little signal, looks like pretty much noise. In the middle, we see a strong signal, that's in the middle frequencies, and towards the right-hand high frequencies, we see, again, no signal. So we know that the signal has a width of thus and so and an amplitude of thus and so. Another thing a spectrum analyzer can do is to separate and resolve complex signals into their base components. So in this picture, you can see that a single signal is actually comprised of multiple signals in the frequency domain. Those are separated in frequency, but they all contribute to the same signal that the analyzer is looking at. Let's do a comparison between the time domain view and the frequency domain view. We'll begin with these three colored signals. You'll see a signal at a low frequency. It's oscillating slowly, a medium frequency, and a high frequency. And if you were to use an oscilloscope, you'd be looking at the time domain window in this direction. And we see that the three waveforms are superimposed on each other. They're all occurring at the same time, and the oscilloscope gives you their composite voltage versus time. And we see a waveform that maybe looks like this. The frequency information is obscured by this view. You can't tell clearly what frequency the different signals that make up this composite signal are at. A spectrum analyzer, on the other hand, looks through a window of the frequency domain and sees the signals in this direction. You can see now that the time view is gone. I don't see timing information now, but I can clearly see that I have three different frequency components that are visible in this window. Sometimes an oscilloscope might be the right tool. When is a spectrum analyzer a better tool? In general, there are a few reasons to choose a spectrum analyzer. One of them is that if you want to see the frequency makeup of a signal, then this is the right way to do it. Another one is the dynamic range is improved through a spectrum analyzer because in the oscilloscope view, you really can't see those small signals very well. They're being dominated by that one large signal. But in a spectrum analyzer, you can easily see low-level signals, even in the presence of large signals, and you have a very high dynamic range, so you can see incredibly small signals. One more good reason to use a spectrum analyzer is that the world of RF and microwaves is often applied to communication systems, and communication systems are almost always frequency banded or channelized. By their nature, those signals are supposed to stay within a certain channel and aren't supposed to leak into adjacent channels, a spectrum analyzer is obviously the right way to make sure that those kinds of specs are being met. A spectrum analyzer can make a lot of different measurements. I'll just briefly say that one very big application area is transmitter test. You've got a transmitter that's trying to intentionally radiate a signal, and you want to check that that signal has the right kinds of properties. A spectrum analyzer or signal analyzer can look at that signal in many different ways and tell you lots of important things about it. Another broad application area is spur search. Spurious means that we have small signals, typically, and not expected or not wanted signals. A spectrum analyzer will help you find them if you didn't know they were there already, and also help you quantify whether they're going to be a problem to your communication system or not. Spectrum analyzers can operate in a couple of fundamentally different ways. This picture denotes a swept spectrum analyzer, and it's really simple to just imagine that you've got a filter shape. This is a tunable, sweepable bandpass filter, and we're going to sweep from the left to the right. And when the bandpass filter passes over a signal that's coming into the input of the spectrum analyzer, then we see a response on the display. Conversely, there's another type of totally different architecture called an FFT analyzer. FFT means fast Fourier transform. That's a mathematical transformation that takes data accumulated in the time domain and transforms it into the frequency domain. So we're going to acquire a large piece of spectrum all at the same time, and then mathematically we'll break it into these individual bins, almost as if we had 100 or 1,000 bandpass filters that were all transforming that energy into filterized or channelized version, and we'll get, in many cases, roughly the same display. There are some pros and some cons of these two techniques, but that is a fundamentally different and sometimes very useful approach to spectrum analysis. I just want to pass over a couple of naming conventions that folks sometimes use. A spectrum analyzer, in the strictest sense, is meant to be an analyzer that shows you input signal amplitude versus frequency. And its fundamental purpose is to look at both known and unknown RF and microwave signals. I'm going to contrast that with a vector signal analyzer. A vector signal analyzer is meant to study modulation. This is usually used to look at an intentional transmitter, an intentional signal that you know there's a signal there, you know what it's supposed to look like, and you're going to use a vector signal analyzer to check and make sure it's doing the right thing. But these days, an awful lot of products that Keysight sells are the combination of a spectrum analyzer and a vector signal analyzer in the same box. Modern technology allows us to implement both sorts of functionality in a single instrument. That's very, very useful. You can be in a spectrum analyzer domain, which is typically magnitude only versus frequency, or you can be doing vector analysis, which is both magnitude and phase of a carrier. Okay, well now let's get to the theory of operation. What is actually inside a spectrum analyzer and how does it work? So here's a simplified and traditional block diagram for a swept spectrum analyzer. Let's start with the input signal. This is the unknown signal you want to know more about. If that signal is really strong, it'll pass through an attenuator, and then it goes through a very important component called a preselector. A preselector is a tunable bandpass filter, and it's going to move across the frequency domain left to right, trying to make sure that the downstream components of the analyzer don't get exposed to signals that you're not looking at that particular moment in the sweep. It selects the frequency that the analyzer is looking at. After going through a mixer, the resulting down-converted frequency, this is the intermediate frequency, the IF frequency, goes through an IF processing chain. Now, what I think is interesting is that this whole section is devoted to understanding what is the amplitude of the input signal. So the IF is no longer moving in frequency, it's a fixed frequency, and all we care about going through this section is the amplitude of the IF, which reflects the amplitude of the input signal. On the other side, the other port of the mixer is being driven from the local oscillator, oftentimes called the LO, And the local oscillator is moving in frequency, so this entire front end will tune across frequency. It'll sweep from left to right and look at frequencies from low frequencies to high frequencies through the mixing operation of the mixer. The ramp generator or sweep generator is what tunes that local oscillator, and that ramp generator also is coordinated with the display so that it pushes the display to paint the display at low frequencies to high frequencies as the ramp changes from low to high signal and the local oscillator moves from low frequencies to high frequencies. And together you get a traditional spectrum analyzer display. So let's zoom in on the mixer. By definition, a mixer is a 3-port nonlinear device. The input port is going to be the green signal of interest. We're going to be mixing that with the LO, the local oscillator port. It is moving across frequency. And then the output is the sum and difference frequencies. The nonlinear characteristics of the mixer give us new frequencies coming out the other side, which are located at the sum of these two frequencies and the difference of these two frequencies. Well, as we execute this sweep, if we had an imaginary signal at this green bar here, at some point the mixing product will have a frequency that just happens to go through the fixed frequency IF filters that are downstream in this chain. And that moment happens when the frequency of the LO is equal to the frequency of the signal minus the IF frequency. So at that magical moment, that's when the IF sees a response, and that's when the analyzer shows you that you've got a signal of a certain amplitude which appears at that particular point during the sweep. So after we've got our IF signal, we'll go through some gain and attenuation adjustments, but then the next significant block in the IF chain is the IF filter, more commonly known as the resolution bandwidth filter or RBW filter. This is a very important control. It gives you a lot of the power that a spectrum analyzer can deliver, especially in terms of resolving multiple signals. So let's imagine that our input signal has two signals to it, a lower frequency and a higher frequency. If the RBW filter is set wide, then you can imagine that both of these signals will stimulate the filter or pass through the filter in a way that's not really distinguishable as the analyzer sweeps from low frequencies to high frequencies. They're both going through that filter in roughly the same indistinguishable time in the sweep. If we were to reduce the bandwidth of the RBW filter narrower and narrower, we'll eventually get to a point where the RBW filter is narrow compared to the spacing of these two signals. And now, as the analyzer sweeps from left to right, we'll be able to paint out the signals individually and we'll be able to resolve them in the frequency domain. Very important control. You would use a narrow RBW filter when you want to resolve frequencies that are closely spaced in the frequency axis. It's also a very important way to reduce the noise that passes through the IF section and winds up being detected. So dropping the noise floor is another important reason to have a narrow RBW. Well, if you have these two great benefits of using a narrow RBW filter, why would you ever want to use a wide one? There are two main reasons to use a wide filter. One is that you can sweep faster with a wide filter. So you can sweep more spectrum in less time if the RBW filter is wide. That's a huge benefit in many applications. The other thing is that sometimes we don't really want the spectrum analyzer to be bothered by minor fluctuations or minor differences in frequency. So with a wide RBW filter, we can allow it to see a wide part of the spectrum at once, and if the input signal is maybe wandering, or maybe we don't care if there are two signals there, we just want to know roughly how much energy is in that part of the spectrum, a wide RBW filter will make the analyzer blind to those differences. The next stop in the IF chain is the envelope detector. In this block diagram, we're going to show that very simply as just a diode detector. And that detector is going to take as the input the IF signal, but strip away all the IF frequency content and give us only just the outline of the amplitude of the IF and give us this sort of signal as we sweep. And we're showing time on the x-axis here, but what that really boils down to is the time during the sweep. We're actually sweeping frequency, and the envelope detector tells us when there's a strong signal or a weak signal in the IF. And then the last stop in this block diagram is the video filter. So now we've got an envelope that's come out of the envelope detector. You can imagine if we're looking at low-level signals that are near the noise floor, even though we've stripped away the IF frequency, we might still see some strong up and down noise characteristics in the amplitude dimension, the vertical axis. So the video filter is essentially a low-pass filter that smooths out that trace, gets rid of those wild fluctuations, and helps us see more accurately what the level of the signal is, and might also help us see responses that are due to very small signals that are near the noise floor. Okay, well, I told you earlier that we were going to walk you through an old-fashioned traditional block diagram, and now I'm going to tell you the truth. The truth is that almost everything in this pink block has been replaced by digital components. What we're going to do now is, with a precision high-frequency ADC, we're going to digitize the IF signal coming from the mixer, turn it into digital words, and now pass that through a digital processing section, a digital IF section that implements all these functions in the digital domain. For example, a digital RBW filter, a digital log amp, and also digital detection or envelope detection. All these things happen now in basically a computer or an FPGA. Notice that this digital IF is also capable of both modes of data acquisition. We can operate it as a traditional swept spectrum analyzer, but we can use the exact same data coming from the ADC, transform it in a slightly different way, and now we have an FFT analyzer all implemented in the same block diagram. Isn't that cool? I'll briefly mention too that other parts of the block diagram have also been enhanced with time. For example, the synthesis and phase noise of the local oscillator has been improved, and corrections that help us get better frequency response. Lots of things have gotten better, but for the moment I'm just going to focus on this pink section. So here we're going to take a closer look at what detection means with a modern digital IF. The first thing I want to make sure that you realize that the ADC is spitting out samples at a much higher rate than we'd ever want to display on the screen of our analyzer. A display of a spectrum trace might typically have 1,000 points to it. But for each one of those dots that we're going to paint on the screen, you might take, well, let's just say 10 or 100 ADC samples, and now you've got some choices to make. Which of those ADC samples do I use, and how do I present those to the display? What we'll do is have some algorithm that tells us how to process the underlying low-level ADC samples and convert that to a bin or a bucket, which is equivalent to one display point. These are called detector types. One detector type is positive detection, and that obviously means that out of these 10 or 100 samples during this time interval, we're going to pick the largest one and choose that one to display. Alternately, a negative detector is going to do the opposite. It'll find the smallest ADC sample out of the 10 or 100 samples and choose that one to put on the screen. Another detector type is sample detection. This is really almost the same as randomly choosing one of the 10 or 100 points in this time interval. What we're probably going to do in practice is just choose the middle sample out of the 10 or 100 samples and display that one. It kind of gives you sort of a random idea of what the signal is doing during this time interval. The last detector type that we'll mention here is the normal detector, also sometimes called the Rosenfeld detector. It's a little difficult to describe in detail, but at a very high level, let me just say that the algorithm that's used to select which ADC samples are put onto the trace is different when the samples are noise-like versus when the samples represent a signal that's present. So the benefit of that is that you get to have a trace that has the best of both worlds. Sometimes when the signal is noisy, you'll get a signal that tells you clearly that you're in the noisy domain. But when there is a strong signal present, then the algorithm will help paint out the picture of that signal response in a way that's appropriate for signals. One more detector type I wanted to mention before we close on the digital IF is just to describe the power average or RMS detector. This is the detector to use when you're trying to measure noise power, Or you have a signal that has noise-like characteristics. In other words, its amplitude is varying wildly all over the place. In this case, you want to do true power representation. The right way to do it is to process every sample. Every single ADC sample within that bin is going into an accumulator, and we will process the square root of the sum of the squares of all those samples. That's RMS, root mean square, and then convert that to a power indication, assuming that we have a 50 ohm characteristic impedance. Very important for noise and noise-like signals. So when it all comes together, the outputs of the digital IF are processed by a computer inside of the signal analyzer. They're sent to a digital display, and you'll get a picture that looks kind of like this. Remember, the LO is sweeping from low frequencies to high frequencies, and when the sum or difference frequency from the mixer passes through the IF frequency, then we get a response that causes a deflection vertically, and we can tell that there's a signal there. With a calibrated analyzer, we can put a marker on that signal. We can tell exactly what its frequency and amplitude are with very good precision. And we're looking at a picture that shows us the whole story. We can easily see that there's a signal that's tens of dBs lower, and we can tell where the noise floor of the analyzer is. We can see everything there is to know about this frequency span. Now let's take a look at the specifications of spectrum analyzers. This is not only to help you do comparison shopping, but it's to help you understand which characteristics of a spectrum analyzer matter to your particular application so you can make the right choice. Today I'm just going to cover the highlights and also some of the specs that are most confusing to people and just call it done at that. We'll start by taking a look at the horizontal axis, the frequency readout accuracy. This really looks like a very complicated spec. Look, it's got these terms that have to do with the marker frequency, the reference, the span, the RBW, and the horizontal resolution. All these different factors contribute to the accuracy of, hey, is my signal that I've got the marker on, is that really at this frequency? How accurately do I actually know that? Although the spec is complex and it looks difficult, in fact it involves some calculations that you have to make to even understand what the accuracy is. The reason it's expressed this way is because you have control over a number of these factors, and you can do something about them by using the analyzer differently, and that's important to realize, and the specs help you see what you can do to improve the accuracy. So for example, the first term here is frequency reference accuracy. That basically reflects the time base, or the crystal oscillator from which all of our frequencies inside the analyzer are synthesized. We do the best job we can of creating a very stable, precise reference, but you know, it's still going to drift with age. It has an aging factor to it. There's still a limit to how closely we can adjust it. There's going to be a temperature stability term to it as well. You can see those factors summarized up here. What you have is a frequency reference accuracy that changes with temperature or time. But you know what? There's something you can do about that. All of our analyzers have a reference input, and if you provide a reference frequency that you think is more stable, more accurate, less susceptible to temperature variations, you can plug it into the rear panel of our analyzers, and now this term is going to be reflective of your reference, not the one that's inside of the analyzer. Likewise, take a look at this term. We have 0.1% of span is a contributor to the frequency readout accuracy. Well, hey, you can control the span. That's the frequency range from the left-hand edge to the right-hand edge of the display, and if you narrow the span, you will reduce the size of this error term. Likewise with RBW and even horizontal resolution, you have control over all those terms. So it's smart to know how they contribute and which ones make a difference for the measurement that you are trying to make. Let's talk about phase noise or noise sidebands. You remember in our block diagram that we had an LO that was mixing with the input signal and gave us an IF frequency. The LO is going to have some noise characteristics. It's going to be, you could say, wandering in frequency or moving rapidly in phase, which creates this sort of back and forth motion on the LO, and that mixes with your input signal and gives us these noise sidebands in the IF chain. You can tell here that this noise product, it is a noisy looking signal. It always appears close to a strong signal, for example, this input signal under test. But the point of this discussion is to realize that these noise sidebands could potentially hide a signal that you're actually trying to look at next to a strong signal. So be aware that if you're trying to tackle this measurement situation, small signal next to large signal, you'll be faced not only with the choice of RBW filters, that's one issue to get right, but you'll also be wanting to take a close look at the noise specs because they could also be limiting your ability to see this little guy here. Now let's turn our attention to the amplitude dimension of a spectrum analyzer. One of the first questions we might want to ask is just how sensitive is that spectrum analyzer? How small of a signal can it see effectively? Sad news is all electronic circuits generate their own noise, including spectrum analyzers. So our block diagram is going to be injecting tiny amounts of noise on top of your input signal, on top of the IF, even on top of the LO signal, and those will be a noise source that has to be understood to determine whether you can make the measurement you're trying to make. Sensitivity is the term we use for the smallest signal that can be measured with a spectrum analyzer. It turns out that when the amplitude of a signal you want to see is exactly the same as the noise floor, which we call DANL, display average noise level, that's one of the most important specs of a spectrum analyzer. When those two are the same, then you will see about a 2.2 dB bump in the response of the spectrum trace. That assumes you have a sufficiently low RBW and video bandwidth filter to smooth out that trace and attenuate the noise on the trace. Using a narrower RBW filter is one way of reducing the noise that goes through the IF section. And here you see a really cool sequence of traces where we took a sweep of a very small signal with a 100 kilohertz RBW filter and then 10 kilohertz and then a 1 kilohertz RBW. And so just narrowing the RBW was enough to reduce the noise going into our detector, and so drops the noise floor where there is no signal present. Obviously, the signal that is present is being measured with the same amplitude as it should be. So we're able to drop the noise floor and we're able to more clearly see the signal by using a narrower RBW filter. What's the price you pay? Speed is probably the primary price you pay. But if you can arbitrarily put the noise floor anywhere you want by changing the RBW filter, what is the meaning of a specification for DANL? So the industry norm is to specify the DANL in a 1 Hz RBW filter. It doesn't even matter if you don't use or don't have a 1 Hz RBW filter. The point is that so that all instruments can be compared equally and fairly, the industry has adopted a standard of specifying DANL as if it were in a 1 Hz RBW bandwidth. Probably the next most important and sometimes one of the more difficult specs to understand is what is the dynamic range? What is the difference between the largest signal that I can see and the smallest signal that I can see? That's called dynamic range and usually expressed in dB. Now I'm going to introduce you to a whole new chart, and we'll build up the concept of how to portray the dynamic range of a signal analyzer. First of all, what is this graph representing on the horizontal and vertical axes? This is not a frequency display. What we're looking at here on the horizontal axis is the power that's hitting the first mixer of the block diagram. So the horizontal axis is power to the mixer, which you can control by adjusting the attenuator and knocking down the input signal. On the vertical axis, our line is going to tell us what the signal-to-noise ratio is. The signal is the thing that you're trying to measure at the input of the analyzer. The noise is the noise floor, or the DANL, of the spectrum analyzer. What does this purple line actually mean? What is it trying to tell us? It's saying that if you have a strong enough signal where you can input minus 15 dBm to the mixer, and if you were to use a 1 kilohertz RBW, then the difference between that minus 15 dBm and the noise floor of the instrument is such that you would have 100 dB of dynamic range. The signal-to-noise ratio would be 100 dB. And then if that power were to be reduced, if you had a weaker signal, then you'll move along this curve here, and the signal-to-noise ratio will degrade because the signal is becoming smaller, although the noise floor of the instrument is remaining constant along this line. What can we do about that? Well, we can reduce the RBW filter. So if I was to switch to a 100 Hz RBW filter, then I can drop down to a lower line, and I still have this sloping line which represents my signal-to-noise ratio as a function of the signal level, but I've dropped to a lower line by using a RBW filter that's narrower and a Danel which is driven lower by that change. Let's talk about distortion. There are several elements in the block diagram that create distortion. One of them is the mixer. So if the signal to be measured has some distortion products here and here, that could be the thing that we're trying to understand. We want our analyzer to tell us what are these distortion products here and here, and how do they relate to the strong signal of interest. But it sometimes turns out that the analyzer itself generates distortion that you didn't want, but it's part of the measurement process, and these distortion products can add to or interfere with the signal distortion products that you're trying to actually measure. And so you're seeing a picture that doesn't truly represent just the input signal, but has contributors that come from the analyzer itself. Two forms of distortion are third order and second order, or two-tone and harmonic distortion. So let's go through those in turn. This set of spectra is typical of an intermodulation measurement. So for that measurement, we're inputting into a device under test, like an amplifier. We might be inputting two tones that are desired, and you want your amplifier to amplify these two signals. But due to nonlinearities of the amplifier itself, you get some intermodulation products which appear here and here. The spacing of these products is exactly the same as the spacing between the two input signals going into your amplifier. So a spectrum analyzer would be the ideal tool to see these intermodulation products here and here. However, the signal analyzer itself will generate its own intermodulation products, and those are indistinguishable from the ones that are generated by the device under test, the amplifier that you're trying to characterize. So it's very important to know how much distortion do I get from the spectrum analyzer, how can I minimize that distortion, what dynamic range do I really have, the dynamic range to see this signal in the presence of these strong signals. This set of distortion products is called third order. It's third order because the outermost products are 2f2 minus f1. The sum of those is you could say 3, a factor of 3, and the left-hand product is 2f1 minus f2. Again, you have a factor of 3 in that set of tones. There's another distortion mechanism, which is simple harmonic distortion. I think probably everybody has seen this before, where the second multiple and the third multiple of the fundamental frequency appears as an output of a distortion mechanism in an amplifier or a mixer or something else. Here again, it's easier to understand, but the truth is that a spectrum analyzer will sometimes generate its own harmonic distortion, known as second order distortion, at the second and third harmonics of the input signal. And if that's the measurement you're trying to make, you want to know, again, what the impact of the spectrum analyzer's distortion will be and how to optimize it. So now we're going to come back to that diagram I introduced a few slides ago, where we have input power to the mixer on the horizontal axis and signal to noise ratio on the vertical axis, only this time we're going to call it distortion. Because at the high end, at high power levels, it's the distortion that's going to limit our ability to see the true signal separately from the distortion products generated by the spectrum analyzer itself. And just like before, we're going to draw some lines on this graph that represent the trade-off between input power to the mixer and the signal to noise or the signal to distortion ratio that you would see on the vertical axis. Okay, so we see on this chart that we have two lines. The purple line represents the second order distortion products, and the blue line represents the third order distortion products. Notice that those two lines have different slopes to them. There's a very good reason for that. When you increase the power to the mixer from your signals under test, this is what you want to measure, the distortion products, which are generated in the analyzer, increase with the level that you drive the mixer at. And it turns out that the degree to which those distortion products increase have different slopes to them. So the second order products, which are the simple harmonic distortion products, those have a slope of 1 to 1. For every 10 dB you increase the mixer level, the distortion products rise by 10 dB. That means that the distortion products are gaining on the signal. In other words, every time you increase the power to the mixer, the distortion products are now 10 dB higher than the signal you were trying to measure compared to the lower mixer level. So you have a slope of 1 to 1. How do you convey this in a data sheet? The standard method is to describe the second harmonic intercept point, SHI. That's a specification of a spectrum analyzer. And that's an imaginary point where this sloping purple line would ultimately intersect the 0 dB distortion level. This is the place where the distortion created by the analyzer is exactly equal to the signal that you're trying to measure in the first place. We would probably agree that the measurement is useless at this point. But it turns out that you don't actually make measurements at this very, very high mixer level. It's pretty much impossible. So in that sense, the SHI spec, the intercept point up here, which looks like it's about plus 30 dBm on this chart, is not actually a usable measurement point, but it describes an intercept point that is standard for all expressions of second order distortion, or SHI. Let's turn our attention to the blue line then. The blue line represents third order distortion. That was the distortion on the left-hand side of this diagram where we're trying to measure intermodulation. Just as before, this is a line which is proportional to input power to the mixer, but this time the slope is different. The slope is exactly twice as steep. We'll see a 20 dB increase in the third order distortion products for every 10 dB increase of power hitting the mixer. So the slope of this line is double the slope of this line. Here again, however, we can imagine that there is some input level at which the distortion products would be every bit as big as the input signal we're trying to measure. Again, at this point the measurement is probably just about useless, but the intercept point where this sloping line strikes the 0 dB distortion line or level can represent a specification called the TOI, or third order intercept line. This is, again, a very important specification for a spectrum analyzer that describes kind of the maximum signal level, or the maximum level to hit the mixer where you can ever dream of making a practical measurement. But probably reality is that your measurement is going to take place more accurately down here. So now we're going to put those two together. And this is what creates the dynamic range concept. We know that if we drop our signal level lower and lower, if we apply the attenuator, then the signal-to-noise ratio will increase higher and higher and higher. We obviously don't want to make a measurement out here because the noise is rising to a point where the signal is harder and harder to distinguish from the noise. On the other hand, we don't want to go too far in this direction. That would be a high signal level or a low value of attenuation, because as we drive the mixer harder and harder and harder, we'll be increasing the distortion products that limit the highest amount of power that we can put into the mixer. So now we have the makings of understanding where is the optimum place to make the measurement. In this V-curve area, here or here, those two, the intersection of the noise line and the distortion line tell you that the best place to make a measurement, if you want to maximize your dynamic range and you're concerned about third order intermodulation products, is right about here. On the other hand, if you're making a measurement where the second order distortion products are your primary concern, you actually want to make that measurement at a slightly different point, which might be here instead. Those are the optimum mixer levels, and because you have control of the attenuator, you can adjust the level of signal hitting the mixer for a certain set of input signal amplitudes. Remember, too, that we can adjust the displayed average noise level, the DANL, by changing the RBW filter to move this line up and down. These two lines tend to be constant. You simply pick the one that's most relevant to your situation, and then your location for the optimum mixer level is achieved by optimizing the attenuator setting. The whole discussion about dynamic range is summarized here. You're talking with your buddy at the coffee stand, and he says, "Hey, what's the dynamic range of your spectrum analyzer?" It's a loaded question, because there is more than one answer to that question. Dynamic range of a spectrum analyzer depends very much on what you're trying to do with it. And so here we see a set of definitions for dynamic range, and let's go through each of those quickly. If you want to know what the dynamic range from the absolute largest signal you could ever input to the analyzer without blowing it up, compared to the noise floor of the analyzer, you might have this dynamic range which you could call measurement range. This is the maximum plausible range you could actually make a measurement in. It turns out there's probably a more realistic definition. For example, the green bar here represents the maximum signal level that you could put into your analyzer before you start to see compression phenomena. This is a little bit different than distortion phenomena. We're just not able to make accurate amplitude measurements beyond the compression point because the IF output from the mixer is no longer linearly proportional to the input power of the mixer. Again, the dynamic range in this sense is from this mixer compression level down to the noise floor. If your measurement is trying to make third-order distortion measurements, oftentimes called intermodulation measurements, then this line, the TOI line, is probably the most important one you have to worry about, because the distortion products you're looking for are going to be created in the analyzer and will mask the thing that you're trying to see. In this case, the signal limited by third-order distortion to the noise floor, that's a new definition now of dynamic range, which is appropriate to the measurement you're trying to make. Likewise, second-order distortion, if you're trying to measure harmonics, would be limited by this range, where the SHI spec and its range to the noise floor is what you want to worry about. And finally, we have another definition which is limited or dominated by the noise sidebands or phase noise of your spectrum analyzer. Okay, we're in the final section of our webcast. We're going to look at just some of the features that I didn't get a chance to talk about until now. Each of these is going to be a very, very brief 1 or 2 slides. It kind of gives you an idea of the wide range of powerful applications that the analyzer is capable of. A very cool feature of our spectrum analyzers is called noise floor extension, which we've abbreviated as NFE. NFE is the idea of reducing the noise floor of the analyzer by mathematically subtracting the noise power that is added by the spectrum analyzer, so it's removed from the signal that you're trying to measure. This works if you can apply enough averaging. So in other words, we're making measurements so near the noise, we have to use lots and lots of averaging to reduce the variance and reduce the noisiness of that trace, and then we can subtract the power that is added by the analyzer. And of course, we have to be able to very, very accurately characterize the noise that's contributed by the analyzer, so we're not adding another error component while we subtract the noise. But we've done that, we've studied it, we've worked at it, and our analyzers can now offer NFE with, in some cases, 8 to 12 dB improvement in the noise floor of the analyzer applying NFE. Our customers love this feature so much that we came along with a later version of it called NF2. That's adaptive NFE. And this is a refinement on the NFE principle, which gradually applies the subtraction process depending on how much averaging has been accomplished over time. So that when low averaging has been accomplished and we want to gradually bring in a little bit of NFE, the trace doesn't look excessively noisy or chaotic. But as the measurement naturally averages and as the trace naturally approaches less variance, then we apply full NFE and get the full benefit of noise floor extension. Another great innovation that's occurred in recent years is alternate methods of acquiring and processing data. To lead into this feature, let's re-review what a swept analyzer does as it sweeps across frequency. So the LO is moving, we put the mixed down signals through an IF section, and we process a spectrum across low frequencies to high frequencies. But if you think about that measurement taking some kind of finite amount of time, you realize that we're actually looking at just one particular frequency at one particular time as we sweep frequency. And what that means is that information was lost. In other words, if a signal appeared briefly during this time interval, even though that frequency was covered by a sweep, it wasn't there when the spectrum analyzer was looking for it. And so this information is lost. There's another acquisition technique based on the FFT, and that's where the analyzer can acquire information over some larger bandwidth, process that in the FFT, and then display it. And you could actually move the LO and acquire another block and process it, and acquire another block and process it. So given enough steps, you can cover the same amount of spectrum width. But again, you're making acquisitions that have a finite bandwidth, and information can still be lost in both the frequency direction as well as the time direction. But the innovation that has made a huge difference to some applications is the real-time FFT data acquisition method. And this is a case where the acquisition is continuous and gap-free. What I've tried to show here is that the acquisitions overlap each other. One acquisition is overlapped in time with the next one is overlapped with the next one, so that there is no gap down the time axis. The analyzer is continuously looking at the spectrum. Now, it's true that the span of the digitizer limits the amount of spectrum, the width of this measurement that we can see at any particular time, but the attribute of being able to see every signal without any time gaps is a very important one for many applications. This gives us the attributes of being gap-free and having a high probability of intercept. The FFT process doesn't even show up in this diagram, this purple block that processes the FFT, because it's happening in the background. It's happening so fast that while we're acquiring this block is being processed for the FFT, and we never skip a beat. There's no need to have a gap between successive acquisitions. In the past, signals that were complex or intermittent or appeared very, very briefly or very unpredictably, you might have had to use peak hold detection techniques, and your spectrum might look like this. If you were lucky, you might have captured the signal. But nowadays, with a RTSA, real-time spectrum analyzer feature, you might get a display that looks like this. Because the analyzer is looking continuously at the spectrum, you can detect signals that are, in some cases, as brief as 3.5 microseconds. That means a signal that's there ever so briefly can be reliably captured by the RTSA feature. We're going to use density and histogram mapping techniques so we can distinguish signals that appear frequently in this part of the spectrum versus those signals that occur very, very briefly, such as these that dance around, appear, and then disappear just as fast. We'll use persistence. That's a display technology that makes brief events stay visible long enough for the human eye to see them. And very importantly, we can now offer a feature called frequency mask trigger, and this lets us freeze this whole display and do a closer examination of signals based on triggering off of a signal that appears only very momentarily in both the frequency and the time dimension. We can, for example, put a trigger around this peak, and only when it occurs do we stop the display and take a closer look at what was going on. Very, very powerful. If you're interested in RTSA, we've got lots more to share with you on Keysight.com. A spectrum analyzer is capable of much more than measuring spectrums. And here are a few examples of measurements that can be made with the same instrument that you would use for spectrum analysis. For example, AM and FM demod. You can do noise figure measurements. That's a common measurement for amplifiers. You're trying to see how much noise an amplifier or a down converter adds to your signal in your DUTS processing chain. We have pulse analysis applications that look at pulsed signals and characterize pulses. There's also a phase noise application that looks at the phase noise of your DUT. A signal analyzer can make that measurement too. All it takes are optional or additive applications that turn your analyzer from measuring spectrums into measuring these other parameters. As technology moves on, customers make use of higher and higher frequencies, so our instruments have also moved to higher and higher frequencies. Just in the last year, the N9041B has become our new flagship. In one instrument, we can cover from 3 Hz all the way up to 110 GHz. The noise floor at these high millimeter wave frequencies is phenomenal, around minus 150 dBm in the 60, 70, 80 GHz range. That's unheard of. And then the bandwidth abilities of the instrument have also increased dramatically with a 1 GHz internal digitizer, or you can use an external digitizer to look at 5 and even in some cases up to 8 GHz of IF bandwidth. We have some alternatives for making those high frequency measurements. For example, this family of smart mixers are based on USB connections, and they can measure up to 110 GHz, but in a more cost-effective way. We support the legacy mixer types as well as mixers from third parties like OML and VDI that interface with our signal analyzers and allow measurements even as high as a terahertz. Modern signal analyzers are capable of vector demodulation. This is when the analyzer is looking at an intentional transmitter, like a communication device of some kind, and trying to assess the modulation quality that you are imposing on that carrier to carry information. This is an in-channel measurement, and it requires vector demodulation, sometimes called IQ demodulation or magnitude and phase demodulation. Our analyzers cover a wide range of standard wireless formats, for example, WCDMA and LTE and Wi-Fi and so forth. And we also have basic constellations covered, for example, QPSK and QAM, among a long list of other modulation types, from bandwidths as low as 40 megahertz and even lower, all the way up to a gigahertz. The Keysight X-Series signal analyzer portfolio has been the star of the show here. We offer analyzers from the economical end of the CXA up to the uber high performance end of the PXA and UXA products. All of them have a common user interface, the multi-touch GUI that Keysight pioneered a few years ago. And all of them offer the same Skippy remote compatibility. Many of them offer code compatibility with their earlier predecessors from prior generations of signal analyzers. Well, thank you very much for listening to this webcast. I hope it's been helpful to you. We have a lot more information to share with you. You can visit these online resources to gather more information, find other webcasts, and attend other videos on YouTube and other social media. Thank you very much. Good luck with your measurements.
Thanks, Dave, for the informative presentation. First question, please comment on sweeping the resolution bandwidth filter and the time it takes to fill the filter and give a correct amplitude. Dave?
Keith, do you want to grab that question?
Okay, yes. This question has a lot to do with radar applications. We get this question. People ask about the rise time of our filter, and a rule of thumb is that the 10 to 90% rise time of the RBW filter is given by the formula 0.7 divided by the RBW, and this helps you figure out what the minimum pulse width can be measured by a given resolution bandwidth. So when the analyzer is sweeping and you've left you're using the auto couple settings, the analyzer will auto couple the sweep time to the RBW so as not to sweep too fast. And then additionally, we do have the fast sweep options, FS1 and FS2, that allow the analyzer to sweep faster than the RBW filter would otherwise be able to sweep. We use a concept that's similar to what radar folks call chirp sweep. So we're able to chirp the sweep essentially, and then we're able to correct afterwards in FPGA, so we can go faster. The FS2 option added more gates to allow us to go even faster.
Thanks, Keith. Second question, when performing IP3 measurements, how can we ensure that the analyzer's mixer is not affecting the overall IP3 measurement?
Now, Keith, I know you're chomping at the bit to answer that question too.
Oh, okay. Yeah. So our signal analyzers have adjustable attenuators and adjustable resolution bandwidth filter settings. So you can essentially increase the internal attenuation until the displayed distortion products no longer change in amplitude. So the analyzer's distortion adds to the distortion products of the device under test, and you increase attenuation until the analyzer no longer affects the measurement. But when you increase attenuation, the noise floor of the analyzer increases, and so you can reduce resolution bandwidth to compensate for that, and you end up increasing attenuation, then decreasing RBW till you get to a certain sweet spot. And then measurement repeatability can also be improved by applying averaging or reducing video bandwidth. Log video averaging can also be used. It causes an under-response in the noise trace, thereby improving the signal-to-noise of the distortion products. And then you have to remember, we have some built-in measurements in the SA mode, and one of the built-in measurements is a TOI measurement that takes care of the settings for you. And then there is an awesome article that Bob Nelson from Keysight wrote for RF and microwave that goes into TOI measurements. So if you do a Google search for RF and microwave Bob Nelson, you should be able to find the article.
Thanks, Keith. Dave, next question is for you. That real-time spectrum analyzer sounded cool in the presentation, but you said it only covered up to a bandwidth of the digitizer. How wide is that bandwidth of the digitizer?
Yeah, great question. So Keysight offers options to put a digitizer of optional bandwidth inside your analyzer, so you can go, you can configure your analyzer to be 40 megahertz or 160 megahertz or 255. We cover up to 510 megahertz of bandwidth with the RTSA feature as an option.
Thanks, Dave. We have time for one more question. The question is, do you have any papers on NFE?
Well, that's a very quick answer. Yes, go to keysight.com. We have papers that describe our approach to NFE and its successor, NF2. You'll learn more about it there.
Thank you, Dave. Well, this concludes today's webcast. Thank you for attending today's webcast brought to you by Keysight Technologies, and have a great day.